The title of my presentation is actually a mouthful. It's about creating immersive content after Moore's law. Okay, well, I know many of you are artists. You may ask yourself, why do I care about this geeky stuff? As a start, let's talk a little bit about what is exactly Moore's law. There are a lot of misconceptions out there. Basically, we understand something doubles every 12, 18 months, or 3 years, and so on and so forth. But what exactly is this something? It could be your CPU computational power. It could be transistors on a chip. It could be coolness of your latest gadget. Also in popular culture as well. But if we really look at the original paper from Moore, what he actually says is that, look at these curves. It represents different curves represents different semiconductor processes. What he says is that assuming you make chips using these different processes, and assuming you can sell as many as you can make, you could decide to put 1 transistor on a chip or 1 billion transistors on a chip. There is a point at which, at that number of transistors on a chip that you're going to make the most money. And that number, that bottom on each of the curve, that observes a power law, and that's the Moore's law. So the reason you have doubling the number of transistors on this chip is because you decide to put that number because it's most profitable. Okay, and it's very interesting that we're observing the end or the death, according to some people, of the Moore's law. Here, I'm showing 2 curves. The right curve is what the Moore's law projected, the number of transistors we should have had on a chip. And the blue curve is actually the number we're having on chips today. And because the y-axis is on a log scale, we're seeing that we're already falling behind, starting from the 80s, and now we're having actually 1/10 what the law predicted we should have had. Also, similar things for DRAM, density. We went from doubling the capacity every less than 2 years to doubling the capacity, in about 7 years. And if you look at the progress of microprocessors over the last 40 years, basically, there's golden age during from the 80s to the 90s with the introduction of the RISC architecture. We're actually going faster than the Moore's law predicted. But right now, from doubling the capacity, every 3 years, we can anticipate, doubling our resources over 20 years. So how do you sell, microprocessors that's improving only by 3% year from year? So what's left? Well, there are a lot of software applications, software optimizations you could do. There's also, the only path forward is through domain-specific architecture. So you really have to know the application, and you have to design your architecture to do those specific things really, really well. But do a few things, but really, really well. Here is one example of software optimization. We heard a lot of people talking about neural networks, artificial intelligence, using Python, so on and so forth. It's very easy to do development, but if you really go through some very fundamental, basic optimizations for even simple things like matrix multiplication from a Python implementation, you could end up with an implementation that's 60 to 1,000 times more efficient. So really, you need to dig deep into the algorithm, and you really need to look at the architecture. Well, the natural question is, why should I care? We're artists, right? We just use machines. And more philosophical question is, must computers really improve that fast? Can the computer industry, just like any other industry, like car industry or entertainment, you only see very slow, gradual improvements year over year? Maybe, in a few years, you can buy a house in the Silicon Valley in Atherton for the same price as a house in Detroit. Good luck with that one. Well, the reason you need to care is because we need to process huge volume data, ever higher resolution. And the processing power just isn't there. And the bandwidth and the memory aren't there. So that's where we want to do a great job in creating the ecosystem. So what RayShaper is doing is we take advantage of deep understanding in both algorithms and architecture, and with a lot of content, of quality, and putting everything together to come up with a system that the content creator could use that meets your needs with the performance, the reliability, and also the availability. So just give you one example. Video encoding is a very difficult task. You have to process a lot of high-resolution, uncompressed data, and if you don't do it very carefully, your memory system basically runs at very low efficiency. So what we have put together, using our deep algorithm knowledge and architecture knowledge, we were the first in the world, actually, doing right now 8K 60 frames a second live streaming of sporting events over 5G networks, live 5G networks. And we have the first truly optical flow-based, real-time, low latency, stitching software available actually in the world with very low latency, 4K, 60 frames a second running on a single GPU card with glass-to-glass latency less than 2 seconds, including networking delay. So here is the 8K 5G streaming I'm talking about. There's this event, the Basketball World Cup, currently in China. And we have the broadcast quality, again, 8K, 60 frames a second, being encoded with a single server running our software with very low latency, streamed over live 5G really deployed networks to parks on a very large, beautiful screen in China. So people are watching it live, even as we speak today. We also did a lot of collaborations with the Montreal Jazz Festival, capturing panoramic video and also light field video as well, both 2D and 3D video with very low latency. So here, so in addition to the encoding and the stitching, the processing, we also wanted to improve the reach of content. We talk a lot about bandwidth, right? The 5G live streaming is over 100 megabits per second. And of course, it's a new 5G network, very few users, so we can do it. But in reality, 90% of the video in the world are being transmitted over TCP IP. Reasonable or not, that's the fact. And the TCP throughput is severely impacted by packet losses, multi-hop, raw changes, and so on and so forth. So if you look at 8K or immersive or volumetric video, you're really looking at, from a previous presenter, over 100, 200 megabits per second we're talking about, right? And in Switzerland, I found this number yesterday, for mobile, it's averaging 15 megabits per second. For fixed broadband, it's just over 100 megabits per second. So we're at the border of being able to stream content. So what can we do? Well, here we're showing the throughput comparison between our technology, RayShaper technology, and what is currently being used all over the world at different locations: Zurich, Los Angeles, Beijing, different places, villages in China, and Bangalore, India. What we're seeing is using the same network and without changing to any software other than the TCP congestion control, we can achieve a very significant improvement in throughput, up to 7 times. The flags, little flags, are the locations that the test has been carried out, and it's currently deployed by IBM, Samsung, other companies. And if you use Twitter, for example, you're using RayShaper technology to transmit video, upload and download. So with 7 times the throughput, you could really fully utilize the bandwidth. You can do many things with the existing network infrastructure. Okay. So we have the encoding, we have the transmission. What about camera systems? Again, as a result of the end of the Moore's law, we can no longer just sit around and expect, the next generation of semiconductor processes will naturally increase the resolution of the camera. So instead, in addition, even if you can build a higher resolution camera, the pixel is going to be really small. The PSNR can be, the signal to noise ratio would be really bad, and there are other artifacts with CMOS sensors as well. So we really, again, need new architecture and domain-specific processing. Here I'm showing a video of our camera. It really is a gigapixel camera, and it's a live camera. The difference between this camera and image you stitched by flying a drone over a city is that when you're flying a drone, and then when there's a car moving, just going at the same speed as your drone, you're going to have the car everywhere. Here, we're stitching live images from up to hundreds of images of cameras in real time, and we can do it very efficiently, and we can result in a equivalent resolution of well over 1 billion pixels. And you can recognize signs, license plates, and other things in real time from kilometers away. So if we could play the next video. I have to click. And when you have multiple cameras, when you intelligently combine information from different cameras, you can also do things like high dynamic range and low lighting enhancement very naturally. And here in this example, of course, we're shooting the concert from far away, kilometers away, and you can clearly see the stage. But it's actually very tricky lighting because the lights, the flashlights, it's very bright, and then it's like the evening is very dark. It's very wide dynamic range. So you can see very clearly, people and very nice texture from, again, very far away. And this is another interesting video. It's a little bit scary, so if you can play it. This is from our office. You play it? Yep. And you can track basically every moving object everywhere, and it gets, both the whole picture and the details. So what's the difference between this system and a super quasi zoom? Well, with a zoom, you will only be able to see one area. You don't get the entire picture at the same time. With this, I can open many windows because the information is there. I compress it very efficiently. I can transmit it, and could be stored and processed. So here's how our system looks like. This is prototype industrial design. The design follows the shape of a beehive. So you can very flexibly put these cameras together, and each one of them is slightly larger than the remote here. It's about the size of a computer mouse. And you can put it in different shapes and form, put in different numbers, very modular, and you can also capture panoramic and light field as well. So here, again, if you could play the video, I have the same camera rig, but with very small number of cameras, we could capture. You could turn off the music. Doesn't. So with only a few cameras, we could capture 6 off. Well, or very strictly speaking, 6 off plus. But you get the stereo version, and creates this immersive experience. And of course, I can only show you a picture because I do not have the render running on the terminal. And even in fairly complicated scenes with a lot of textures, with traffic, with cars, people moving, it still gives you very nice quality. And again, I want to show you with the camera array. Here I'm showing 4 pairs of comparisons on the left and on the right. So you see 4 pairs. Is it running? No. Some problem with the video. But what I'm showing here is the left and the right. On the right-hand side, oops, sorry. If you, yeah, just go to the very end. Just, yeah, so, no, a little bit further. Yeah, just right here. So I'm showing here, left and right. You could see some stuff in there, captured by a professional-grade sensor. And on the right, 2 sensors, the same type of sensor. Is not a high sensitivity sensor. It's the same sensor, but use two of them. And traditional technologies for HDR, for low lighting enhancement, or flash, or infrared doesn't work at this range, at over several kilometers or over an area of 20 square kilometers. But with this technology, you could get enhanced monitoring of a large area continuously and being able to transmit a video to your data center. So what about audio? Of course, you also want 3D ambisonic audio. Traditionally, these audios are produced manually. You have to manually match, drag and drop the audio files to different locations and basically annotate the video. But with our technology, because we have the depth information, we have AI-based recognition for both the instrument, both visually and through audio profiles, we could automatically match the audio files and different locations because we have the depth information, directional information as well. And that this allows you to produce 3D level 3 ambisonic video automatically live. So instead of a manual process takes very long time, we could do this for live streaming as well. So in summary, what is RayShaper? Well, it's a Swiss-based company. It has a hardware system that we're building using very modular, very high quality cameras. The cameras could be configured in different ways to give you very high resolution panoramic video or 6-stop light field capturing. The post-production system can do the stitching, the encoding, the transmission, the storage, and searching, and stuff like that. At very high quality, very high efficiency, and of course, we have a training program that shows you how to use these tools. And we're also launching this thing we call RayShaper HIP, which stands for Heritage Immersive Platform. What it does is basically we want to preserve a library of immersive content for things we really want to preserve, like World Heritages, like events, or the World XR Forum at its 50th version. And we can look at 50 years ago how many of the predictions we made actually came true. So through these systems, hopefully we would be a contributor to the development of the ecosystem for XR, and you may ask, well, when is this available? Well, you could contact me and my partner, Professor Ibrahimi. So we'll be happy to point you to the right direction. Thank you very much.